Hello, this is Dr. Brown, and this video we're going to get into our first unit or first part of the Introduction to Modeling unit. We're going to be talking about functions in general, and in particular, we're going to look at linear modeling. This is on page 271 to 278 in your textbook. First, we're going to get into some definitions. A function is a rule or correspondence that assigns to each element of a set called the domain to another element in a second set called the range. We could call one element, say x1, and it might be assigned to another number in the range called y1. And we could do this like up all the way to x20, y20. And it can be assigned to exactly one element. Exactly is very important. In other words, x1 gets assigned to y1, but x1 does not get assigned to, say, y10 also. It's a complete one-to-one correspondence. It can be defined by a set of ordered pairs, like x1, y1. A diagram, a table, a graph, an equation, or just a verbal description. The set of the first elements of the function or the point or the inputs is called the domain. The variable representing elements in the domain is called the independent variable. And the range, which are often associated to be the y values, is a set of all second elements of the function or the outputs. The dependent variable is a variable representing elements in the range. We could look at a function sort of like this, in which we have a function generator. In which you put an input in, and it could be called x or any other variable you want to. And this is called the domain. And for each x, you get an output f of x, which you might call y. So the output is a range, the input is the domain. Now, it's very important to realize that for any value of x, like x1 in this graph, you get one and only one value, y1, corresponding to that one input. So if you look at a graph of a function, it must pass a vertical line test. For instance, here is a function, and every vertical line you put through the function only touches the line or graph at one point. Now, here's a nice looking curve here. In fact, it looks like a parabola flipped over. It's a nice smooth curve, but it's not a function, because if you do put a vertical line through any point, it touches the graph twice. Here is another nice looking graph, which is an ellipse. It's not a function because it doesn't pass the vertical line test. Now, we're not going to get into everything you see here, but I'm sure if you look on the internet and looking any textbook on math, you're going to see all kinds of functions. Every one of these is a function. If you look at it, it has an x variable and a y variable. Each one of these passes a vertical line test, and there are all kinds of shapes of functions. And we're not going to get into every one of these. In fact, we're going to look at least in this lesson, 4 functions, just to get you familiar with what I call the most important functions in the world. So before we get into linear function details, let me tell you about the 4 most important functions in the whole world. I'm excited about these because each one of these is very important, and much of what we have in the modern world would not be possible unless we understood these functions. Now, the first one I'm sure you're very familiar with. It's a linear function. The graph is a straight line. For any value of x, you have only one value of y. I'm sure you've heard the equation of a linear function, y equal mx plus b, in which m is a slope and b is a y-intercept. We'll get into this later. And a linear function can be so important in so many applications. It could tell you how much your bank account might be growing if you're putting a set amount in every week or every month, and it will go up like a straight line. Now, the second most important function, I think, in the world is a quadratic. And the graph of a quadratic obviously has x squared in it. We're not going to get into all the details of this right now until the next lesson. But a quadratic has, looks like a parabola. It can be turned up this way, or it can be turned this way. And it describes so many phenomena in the real world, like if you throw a ball up, what kind of trajectory it takes. Turns out that I put up about 10 satellites and rockets over a period of 24 years. And when I worked on the space shuttle, I remember seeing this exhaust coming from the space shuttle as it goes into orbit. And obviously all the smoke sort of obscures the trajectory, but I guarantee you it is a parabola that could be described by a quadratic. Now, another very, very important function, which you've already been into in a previous section, is an exponential function in which the variable is in the exponent. And an example that we already worked are future value equal present value times 1 plus r over n to the nt, where the variable here is time, and the variable is in the exponent. And when you've got something that grows exponentially, it grows very quickly, very fast. And we find exponential functions in finance, banking, biological systems, and all kinds of chemical systems. In fact, an exponential function could describe how microbes grow very quickly. I just can't find the time to go into every possible use of a exponential function. Now, the next one is a function that I've been closely related to all my life, almost since I was an amateur radio operator when I was about 12. And it's a sinusoidal function. And we're actually not going to study the sinusoidal function in this course, but I just had to mention it because it's a function that oscillates up and down at a certain rate and just repeats itself forever and ever. And I'm going to tell you in a second why it's so important. Notice if you change the value multiplying the t from 1 to 3, you get 3 times as many oscillations in a given period. And if you go up to say 15, you get 15 times as many. And why this is so important is that these sinusoidal functions carry all your cell phone calls, your photos, videos, Instagrams, your texts, everything you send on the network. Your cell phone itself, the one you're probably using right now, has a sine wave that vibrates at 800 million cycles per second. And on this rides your videos, your movies, your FaceTime calls, your phone calls, your texts. And you would not be able to do this without our understanding of this kind of sine wave. It's what makes wireless possible. Look at, here's an example. You could be at a football game or a soccer game using your cell phone. You could be connected to a cellular network. You could be walking around with your cell phone. You could be at your home. You could be anywhere. But every one of these connections are made possible by a sine wave. And if we go into orbit and look at some of the satellites I worked on, every one of these satellites connects to the Earth and also between them with sine waves carrying the high-speed data that we have come to depend on. Now, that's just a sort of an introduction to sine waves. Now we're going to get into linear functions. So that's a function whose graph is a line, is a linear function, just a straight line. A linear function is a function that can be written in the form y equal mx plus b. And in functional form, you would say f of x equal mx plus b. So if you wanted to find out the value when x equals 5, you just put in a 5 everywhere you see an x. And of course, if you knew what the b was and the m was, you would be able to calculate f of 5. So here m and b are constant, and f of x is the notation we use to symbolize a function. X and y can be replaced by any other variable. For instance, in the sine wave we were talking about, t would have been a variable. In other words, what is the value of that signal at any given time? So we can use any symbols, x and y, z, w, or anything you want to. Now here's some more definitions that you'll need to understand. The points where a graph crosses or touches the x-axis. Let's just draw the axis of a graph. So where it crosses the x-axis, notice that's where y is 0, or the y-axis where x is equal to 0. They're called the x-intercepts and the y-intercepts, respectively, of the graph. You can find the x-intercept of a function by substituting 0 for y and solving for x. And the y-intercept of a function can be found by substituting a 0 for x and solving for y. Now, as an example one, to find the intercepts of the graph of the equation 2x minus 3y equal 12, we're going to find the intercepts and graph the function. First of all, the x-intercept. We'll set y equals 0 in the equation, and then write 2x minus 3 times 0 equal 12. 2x equal 12. So x is equal to 6. So the x-intercept is 6 and 0. That'll be a point on our graph. And the y-intercept is where x equals 0. So now we plug into the same equation, x equals 0, 2 times 0 minus 3 times y equal 12. And we get minus 3y equal 12. Divide by minus 3. And we get y equal minus 4. So the y-intercept is 0 and minus 4. So now we want to graph these functions, graph these points. So first point will be 0 and minus 4. The other, it would be 6 and 0. And if you're doing this just by hand, you could just draw a straight line between. So on the next slide, I've drawn a neat line between the 2 points. And this is a function or graph 2x minus 3y equal 12. Now, let's talk about the slope of a line. The slope of a line is a number that measures the steepness of the line. In the graph we saw a while ago, we saw the skier trying to get up the slope of a pretty high mountain with a pretty high slope. A definition of slope is generally the vertical change, which is called the rise, divided by the horizontal change, which is the run. As you go from, say, here to here, from this point to this point. That is the rise, and the amount the x changes is the run. So it's called the rise over the run. So if a non-vertical line passes through the points x1, y1, and x2, y2, then the slope can be calculated by calculating y2 minus y1 over x2 minus x1. It's also equal to y1 minus y2 divided by x1 minus x2, but it's not equal to y2 minus y1 over x1 minus x2. That the initial point has to either be the very first or the very last in order to calculate the rise over the run. I would always stick with y2 minus y1 over x2 minus x1. Just don't reverse them. Okay, find the slope of the line passing through the points -2, -3 and 2, and 5 and -4. Well, the slope is equal to y2 minus y1 over x2 minus x1. Let's go ahead and call this x1, y1, and this x2, y2. And now we plug in y2 is -4 minus y1, which is 2, divided by x2, which is 5, minus x1, which is -3. So this is -6 over 8, which reduced to lowest terms is -3/4. So it asks us, what does the slope mean? It means that for every 1 unit, x increases. So when the x value goes up 1 unit, y decreases by -3/4 unit. So if you graph this, it's going to be going down. Now, slope and y-intercept. As we said, we can draw or write the equation of a linear function by y equal mx plus b. The slope is m, and the y-intercept of the graph is b. Okay, let's go ahead and write down y equal mx plus b. Is a slope-intercept form of a line, and it asks us to determine the slope and y-intercept of the line. Well, if it's written down like this, y equals 7x minus 12, it's already in the form we're interested in, and you just simply say the slope is equal to 7, and the y-intercept is -12. Of course, you can always put x equals 0 in to get the y-intercept, and obviously it's -12. Now, if you see the line written like this, it's not in the form y equal mx plus b. So we have to solve for y. So let's go ahead and write 2x minus 3y equal 12. That subtract 2x from each side. And now we get minus 3y equals, I'm going to go ahead and put the minus 2x first and then add the 12 to it. All we did was just add these two variables. And so we have minus 3y equal minus 2x plus 12. So I'm going to divide each side by minus 3. So I'm left with y equal 2/3 x minus 4. So now we have it in the slope-intercept form. And so the slope is equal to 2/3, and the y-intercept is minus 4. Another example, a business property is purchased with a promise to pay off a $60,000 loan plus $16,500 in interest on this loan by making 60 monthly payments of $1,275. The amount of money Y remaining to be paid on this loan is reduced $1,275 each month. Although the amount of money remaining to be paid changes every month, it can be modeled by the linear equation. And the linear equation is y equals 76,500 minus 1275x. And it's pretty easy to see that this works. If x equals 0 and you haven't paid anything, you have $76,500 that you still owe, and each month it decreases by $1,275. So we want to find the x-intercept and the y-intercept of the graph of this linear equation. And then we want to interpret the intercepts in the context of this problem. That really means we're going to look at the domain and range to look at the values of x and y that make sense. And so how should x and y be limited in this model so they make sense? And we're going to use the intercepts to sketch the graph of the given equation and then find the slope of the line using the intercepts. Now notice, we already know the slope is minus 1275, because this is the form y equal mx plus b. So the m is minus 1275. Okay, so we want to find the x-intercept and the y-intercept of the graph of the linear equation. That's right, y equal 76,500 minus 1275x. The x-intercept we set y equals 0. and we get zero equal 76,500 minus 1275x, and add 1275x to each side, and we get 1275x equals 76,500. So x is equal to 76,500 divided by 1275, and that is 60. So the x-intercept is 60 and 0. Now the y-intercept we'll set x equals 0, and we get y equal 76,500. So the intercept would be 0 and 76,500. So here are the two intercepts. Now, let's interpret the intercepts in the context of this problem. The y-intercept which is 0 and 76,500 is the starting loan amount. The x-intercept which is 60 and 0 is the month the loan is paid off. So the question, how should x and y be limited in this model so that it makes sense? Well, the loan, outstanding loan, is going to be between 76,500. You're never going to owe more than the starting amount. And when it gets paid off, it's not going to go below 0. And then the months are going to be between 0 and 60. You're not going to keep paying after the 60th month. So now let's put in the intercepts, which you'll recall was 60 and 0 and 0 and 76,500. So here we have a sketch of the graph of the given equation. And remember, the equation was y equal 76,500 minus 1275x. And so this represents the Y loan balance in dollars versus the month that you've been paying. So you start out at 0, you have the full amount of the loan owed. After 60 months, you get down to 0 that you owe the bank. And it said find the slope of the line using the intercepts. We already know the slope of the line, but the slope is going to be the rise over the run. Well, the rise is minus 76,500, and the run is 60. So the slope is minus 1275, which we knew already. Now we're going to talk about a little bit more about the slope-intercept form of a line and the constant rate of change. The equation of a line with slope m and y-intercept b is y equal mx plus b. The rate of change is m, which is the slope of the graph of the function. The rate of change describes how much the output changes for every input unit. In applied context, m is the rate of change, and b is the initial value when x equals 0. We have an equation here, and the notation is h of x as opposed to f of x. And it's the percent of Hispanics in the U.S. population modeled by this equation using data from 1990 through 2050. And it is h of x is equal to 0.224x plus 9.01. What is the slope of the graph of the function? The slope is 0.224 per year. So each year, the percent of Hispanics increases by 0.224% per year. And what does the slope tell us about the annual rate of change? Just what I said. The increase in percent of Hispanics is 0.224% per year. Example 5. An appliance repairman charges $60 for a service call plus $25 per hour for each hour spent on the repair. Assuming the service call charges can be modeled by a linear function of the number of hours spent on the repair, write the equation of the function. So y is going to be equal to the cost, and let x equal the number of hours spent. It's very simple to see that you're going to always pay $60 no matter what the length of time is he comes and spends on the repair, plus $25 times x, which is the number of hours spent. So writing it, turning it around, we got y equal 25x plus 60. Now, another way to write the equation of a line is to have a known point and to know what the slope is. You can then write the equation of the line as y minus y1 equal m times x minus x1. So given a point and the slope, m, you can write the equation of any point, and you know a line is going through with a certain slope m. This is the equation. Example, write the equation of a line through the point 3 and minus 7 having a slope of minus 2. Well, you need to have your equation handy. Y minus y1 equal m times x minus x1. So this is x1, this is y1, and m is equal to minus 2. So we write y minus y1. Y1 is minus 7 equal m, which is minus 2, times x minus x1. X1 is 3. So now we just need to simplify this, and we get y plus 7 equal minus 2x plus 6. Subtract minus 7 from each side, and you get y equal minus 2x minus 1. Now, here's an example that gives a number of drinks and the resulting blood alcohol percent for a 180-pound man. And here is the definition of one drink. I'll let you read that. And so for 3 drinks, the blood alcohol percent is 0.07. For 4 drinks is 0.09, and so forth and so on. They want us to write an equation for the blood alcohol content versus X, the number of drinks. Well, we can, let's say the first point here is X1 and Y1. The next point could be X2 and Y2. Notice as X goes from 3 to 4, Y goes from 0.07 to 0.09. So the slope is 0.02. And we're going to let X equal number of drinks and Y equal the blood alcohol content. So we're going to use the equation y minus y1 equal m times x minus x1. And y minus y1 is 0.07, is equal to the slope 102 times x minus x1. X1 is 3. this should be y minus y1, which is y minus 0.07. So we got y minus 0.07 equals 0.02x minus 0.06. So add 0.07 to each side, and you get y equal 0.02x plus 0.01. So this is the equation for the blood alcohol content versus the number of drinks that you take. The last example is a number of people and millions in prisons or jails in the U.S. as it grew at a constant rate from 2001 to 2013, with 1.345 million incarcerated in 2001 and 1.570 million incarcerated in 2013. And we want to answer the questions here. What's the rate of growth of people incarcerated from 2001 to 2013? We want to write a linear equation that models a number n of prisoners as a function of the year x, and then use a function to predict the inmate population in 2017. Well, the first thing I'm going to do is look at the first point, which is the year 2001, with 1.345 million. Instead of, we're going to eventually call this n, but I'm going to call the number of inmates incarcerated are going to be, we'll call it y, because it's easier to use a formula that way. So we have x1 and y1 for 2001, 1.345, and then for 2013, the last year that we knew had 1.570 million. So now we want to calculate the slope of this line that we're going to draw. So m is equal to y2 minus y1 over x2 minus x1, which is 1.570 minus 1.345 divided by 2013 minus 2001 is equal to 0.225 divided by 12. And you need to use your calculator, and you get 0.01875, and that's million per year. So now we have the slope. Now we want to write the linear equation that models a number n. We're going to call this y to start with. And then we'll call it n. It doesn't really matter. So the equation would be y minus y1 is equal to m times x minus x1. And so y minus y1 is 1.345, is equal to m, which is 0.01875 times x minus x1, which is 2000 So simplifying this, we get y minus 1.345 equal 0.01875x minus, be real careful when you multiply all this out, and you get minus 337.51875. And then we're going to add 1.345 to each side to solve for y, and we get y, which is going to be the n, the number of incarcerated prisoners, is going to be 0.01875x minus 36.17375. And this is the equation we would use. And so now we have n equal y is 0.01875x minus 36.17375, and y in the year 2017. We plug in 2017. Minus 36.17375. And that is equal to 1.645 million. So that's the number of incarcerated prisoners in the year 2017, predicted by the linear model. And that's all of this video.